In December 2025, astronomers stared at their screens in disbelief. The James Webb Space Telescope had just transmitted an image that shouldn't exist. A galaxy, perfectly formed, spiraling with elegant arms. A cosmic twin of our own Milky Way. But there was a problem, a massive problem that shook the foundations of everything we thought we knew about the universe. This galaxy, named Alaknanda, exists in a time period when such structures were supposed to be impossible. We're looking at an image of the universe just 1.5 billion years after the Big Bang, an infant cosmos. Yet here lies a fully mature galaxy, complete with sweeping spiral arms and a brilliant central bulge. Cosmologists around the world immediately recognized what this meant. Either our observations are wrong, or something fundamental in our understanding of cosmic evolution has been missing all along. This is not just another space discovery. This is a potential crisis in cosmology, and it's forcing scientists to ask uncomfortable questions about the very origins of structure in our universe. To understand why Alaknanda is causing such profound disruption in the scientific community, we need to journey back to our fundamental understanding of cosmic time. The Big Bang occurred approximately 13.8 billion years ago. In those first moments, the universe was a seething plasma of elementary particles. No atoms, no molecule, certainly no galaxies. For nearly 400,000 years, the cosmos was opaque, filled with hot ionized gas that scattered light in every direction. Only when the universe cooled enough for atoms to form did light finally break free, creating what we call the cosmic microwave background radiation. The era of galaxy formation supposedly began gradually. According to the Lambda cold dark matter model, our standard cosmological framework, the first galaxies were small, irregular, chaotic collections of stars. These proto-galaxies would merge over billions of years, growing larger and more complex through violent collisions and gradual accretion of matter. Spiral galaxies like our Milky Way were thought to be late bloomers in cosmic history. The conventional timeline suggested these elegant structures required at least several billion years to develop. The physics seemed straightforward. Dark matter halos would form first, creating gravitational wells. Gas would fall into these wells, compress, and ignite into stars. Over time, rotation would flatten the distribution into a disk. Density waves would create spiral arms. Central regions would form bulges as stars accumulated. This process was calculated, modeled, and verified through countless simulations. The timeline was clear. Spiral galaxies were mature structures, requiring the patient work of cosmic time to sculpt their graceful form. Looking at our own Milky Way, we see a galaxy aged nearly as old as the universe itself, having taken over 13 billion years to develop its current majestic spiral structure. The earliest galaxies we had observed before Alaknanda were small, irregular, and often clumpy. They looked nothing like the grand spiral galaxies that dominate the modern universe. Everything in our theoretical framework indicated that at 1.5 billion years after the Big Bang, we should be seeing galactic building blocks, not finished cathedrals. The theoretical framework for galaxy formation rests on several pillars of modern physics. First, there's the cosmic web, a large-scale structure predicted by simulations of dark matter distribution. In this model, dark matter, which comprises approximately 85% of all matter in the universe, forms filaments and nodes where galaxies eventually form. The process begins with tiny quantum fluctuations in the early universe, amplified by cosmic inflation. These density variations, imprinted in the cosmic microwave background, become the seeds from which all cosmic structure grows. As the universe expands and cools, regions of slightly higher density attract more matter through gravitational attraction. Dark matter dominates this process because, unlike normal matter, it doesn't interact with radiation and can begin collapsing earlier. The theory of hierarchical structure formation suggests galaxies grow through a bottom-up process. Small structures form first, then merge to create progressively larger objects. Computer simulations running this scenario forward in time successfully reproduce many features of the observed universe, from the distribution of galaxy clusters to the cosmic web itself. Within this framework, spiral galaxies present special challenges. Their ordered structure requires specific conditions. A spiral galaxy needs a rotating disk, which forms when gas falls into a dark matter halo and conserves angular momentum. The spiral arms themselves are not permanent structures, but density waves, regions where stars and gas bunch up temporarily as they orbit the galactic center. Creating this level of organization demands time. The gas must settle into a stable disk, cooling enough to allow star formation, but remaining dynamically active. Feedback from supernova and active galactic nuclei can disrupt this process, ejecting gas and preventing star formation. The balance is delicate. Too much feedback, and the galaxy remains chaotic. Too little, and stars form too rapidly, exhausting the gas supply before a proper disk can form. Moreover, early universe conditions were thought to be hostile to spiral formation. The universe was denser, and galaxy interactions were more frequent. Mergers, while necessary for growth, were believed to destroy delicate spiral structures. Only as the universe expanded and galaxies became more isolated, could stable spirals finally emerge. The Hubble Space Telescope had reinforced this picture. Its deep field observations showed that distant, young galaxies looked different from nearby, older ones. High redshift galaxies appeared irregular, clumpy, and chaotic. Spiral structures seemed to emerge gradually, becoming common only in the more recent half of cosmic history. This narrative was consistent, well-tested, and broadly accepted across the astronomical community. Then James Webb looked deeper, with unprecedented infrared sensitivity, and found Alaknanda. The discovery came from an unexpected source. While NASA and the Space Telescope Science Institute operate the James Webb Space Telescope, astronomers from around the world submit proposals to use its precious observing time. Dr. Rashi Jain and Dr. Yogesh Wadedekar, researchers at the National Center for Radio Astrophysics in Pune, India, were analyzing deep field observations targeting a region in the constellation Sculptor. They were searching for early galaxies, hoping to understand how the first stellar populations emerged from the cosmic dark ages. The James Webb Space Telescope's near-infrared camera captured photons that had traveled for over 12 billion years to reach us. Due to the expansion of the universe, light from distant objects is stretched to longer, redder wavelengths. What began as visible or ultraviolet light from young stars is transformed into infrared radiation by the time it reaches our telescopes. This is where Webb excels. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb sees the universe in infrared, allowing it to peer farther back in cosmic time than ever before. As the data was processed, one object immediately stood out. Among the various galaxies in the field, a particular structure exhibited unmistakable morphology. Two sweeping spiral arms, clearly defined, a bright central bulge, a disk structure spanning approximately 30,000 light-years across. The researchers measured its redshift at approximately 6.7, corresponding to light emitted when the universe was just 1.5 billion years old, roughly 11% of its current age. The initial reaction was caution. Could this be a projection effect? Sometimes, multiple galaxies aligned in space can create the illusion of structure, but detailed analysis ruled this out. The spectroscopic data confirmed this was a single, coherent object. Could it be a foreground galaxy masquerading as a distant one? Again, no. Multiple independent measurements confirmed the redshift. This was genuinely an ancient galaxy. As word of the preliminary findings spread through the astronomical community, skepticism was immediate and intense. Peer review began in earnest. Other teams requested access to the data. Alternative explanations were proposed and tested. Was the spiral structure real, or an artifact of image processing? Deep analysis of the point spread function and noise characteristics confirmed the spiral morphology was genuine. The galaxy exhibited clear rotational velocity patterns, consistent with an organized disk structure. The two spiral arms weren't random features, but coherent structures, extending thousands of light-years from the galactic center. The star formation rate was measured at approximately 20 times that of the current Milky Way, indicating vigorous stellar production. The stellar mass estimate reached around 10 billion solar masses, comparable to substantial galaxies in the modern universe. Every test confirmed the same shocking conclusion. This was a fully formed, grand design spiral galaxy, existing in an epoch when such objects should not yet exist, according to standard models. The naming of the galaxy carried deep cultural significance. Dr. Jain and Dr. Wadedekar chose Alaknanda, a Himalayan river in northern India. In Indian mythology, the Milky Way is associated with the celestial Ganges, a river flowing through the heavens. Alaknanda is one of the primary headwater streams that forms the Ganges, making it a fitting name for a galaxy that resembles our cosmic home. The choice reflects not just poetic sensibility, but scientific parallel. Just as Alaknanda is a source river that eventually becomes the mighty Ganges, this ancient galaxy represents an early example of the grand spirals that would later populate the universe. The paper detailing the discovery was submitted for publication in December 2025 and immediately generated intense discussion. Observatories around the world began requesting follow-up observations. The Atacama Large Millimeter Array in Chile targeted the galaxy to measure its molecular gas content, crucial for understanding ongoing star formation. Ground-based telescopes with adaptive optics attempted to capture additional details, though at such vast distances, even the most powerful Earth-based instruments struggled to match Webb's capabilities. The data revealed additional intriguing details. The galaxy's color profile showed evidence of both young, blue stars in the spiral arms and older, redder stars in the central bulge. This suggested a complex star formation history rather than a single burst of stellar creation. The spiral arms themselves showed knots of particularly intense star formation, each region containing millions of young, massive stars, pouring ultraviolet radiation into the surrounding gas. What made Alaknanda particularly puzzling was not just its existence, but its apparent maturity. This wasn't a protospiral, showing the first hints of structure. This was a fully realized grand design spiral galaxy, virtually indistinguishable in morphology from modern spiral galaxies like M51 or M81. If you placed an image of Alaknanda next to an image of the Milky Way and removed the label, even professional astronomers would struggle to identify which was the ancient galaxy and which was our mature local structure. The rotation curve, derived from spectroscopic observations, showed the characteristic flat profile expected of galaxies embedded in dark matter halos. The central bulge exhibited properties consistent with a population of older stars, suggesting that even the bulge had sufficient time to form and evolve. Every measurable characteristic pointed to the same impossible conclusion. Alaknanda was an old galaxy, appearing in a young universe. The implications of Alaknanda's existence rippled through multiple areas of astrophysics and cosmology. First and most immediate is the challenge to galaxy formation, timescales. If a galaxy can assemble a mature spiral structure in just 1.5 billion years, our understanding of the assembly process is incomplete. Several potential explanations have emerged, each with profound implication. One possibility is that star formation in the early universe was far more efficient than current models predict. If the initial generation of stars formed more rapidly and in greater numbers, the timeline for galaxy assembly could be compressed. However, this raises new questions. What physical mechanisms would enable such efficiency? The early universe had lower metallicity, meaning fewer elements heavier than hydrogen and helium. Current star formation theory suggests low metallicity should make star formation less efficient, not more. Another hypothesis focuses on dark matter. If dark matter halos formed and reached high densities more quickly than simulations predict, they could provide the gravitational scaffolding for rapid galaxy assembly. Some theorists have proposed modifications to dark matter properties, suggesting it might be slightly self-interacting in ways that enhance early structure formation. However, such modifications must be carefully calibrated to avoid contradicting other successful predictions of the standard dark matter model. A third avenue explores the role of supermassive black holes. Recent Webb observations have revealed surprisingly massive black holes in the early universe. If central black holes formed quickly and grew rapidly, their gravitational influence could help organize galactic structure. The jets and radiation from actively feeding black holes could also shape gas dynamics in ways that promote disk formation. Some researchers suggest that cold gas streams, filaments of dense gas flowing along the cosmic web directly into galaxies, could deliver material more efficiently in the early universe, rather than gas slowly accumulating and settling. These cold flows might rapidly build up galactic disks, bypassing the lengthy settling time usually required. Each explanation has strengths and weaknesses. None perfectly resolves all the puzzles. What's becoming clear is that the early universe was more dynamic, more efficient, and more capable of rapid structure formation than our previous observations indicated. Alaknanda is not alone. Webb has discovered numerous other surprisingly mature galaxies in the early universe. Each discovery adds weight to the growing realization that something fundamental in our models needs adjustment. Critically, this is not a crisis that breaks cosmology. The Big Bang model remains robust, supported by multiple independent lines of evidence. The cosmic microwave background, the abundance of light elements, the expansion of the universe, all these pillars of modern cosmology remain unchallenged. What Alaknanda challenges is our detailed understanding of how structure forms within that expanding universe. It's a second-order problem, but one with profound implications. Understanding how galaxies form is essential to understanding our own origins. Every atom in your body except hydrogen was forged in stars within galaxies. The story of galaxy formation is ultimately our story. The astronomical community has responded to Alaknanda with a mixture of excitement and intense scrutiny. Some researchers see it as an expected outcome of improved observational capabilities. Every time we build a more powerful telescope, we discover unexpected phenomena. The universe is under no obligation to match our predictions. Others view it as evidence that our simulations, while sophisticated, still miss crucial physics. Computer models of galaxy formation must simplify enormously complex processes. They include prescriptions for star formation, feedback from supernova and black holes, and the behavior of gas under various conditions. Each prescription contains assumptions. Perhaps those assumptions, calibrated on the nearby universe, fail in the extreme environments of the early cosmos. A more radical interpretation suggests we're seeing evidence for variation in the fundamental constants or laws of physics across cosmic time. While mainstream physics strongly resists such ideas, some theorists propose that the strength of gravity, the mass of fundamental particles, or other constants, might have been slightly different in the early universe. Such changes could dramatically accelerate structure formation. However, this explanation faces significant challenges, as any variation must remain consistent with precision measurements of the cosmic microwave background and Big Bang nucleosynthesis. More conservative researchers emphasize the need for larger samples. Alaknanda might be an outlier, a statistical fluke. Grand design spirals might be extremely rare at this epoch, with Alaknanda representing a 1 in a million coincidence. Only by surveying larger volumes of the early universe can we determine whether such galaxies are exceptional oddities or indicative of a widespread population we simply hadn't detected before. The debate reflects healthy scientific discourse. Extraordinary claims require extraordinary evidence. Webb has provided extraordinary observations. Now the community must work to determine what those observations truly mean for our understanding of cosmic evolution. Before we continue exploring the implications of this discovery, I want to hear from you. If you could see a galaxy forming in fast forward across billions of years, what do you think would surprise you most? Would it be the speed of star formation, the way spiral arms develop, the role of dark matter? Drop your thoughts in the comments below. And if you're finding this journey into the mysteries of the early universe as fascinating as I am, hit that like button. It helps this video reach more space enthusiasts like yourself who want to dive deep into the real science behind these discoveries. Your engagement genuinely matters in bringing complex astrophysics to a wider audience. Now, let's explore what comes next in our quest to understand these impossible galaxies. The discovery of Alaknanda opens new frontiers for observational astronomy. James Webb's mission is planned to continue for at least another decade, and possibly longer. Future observing programs will specifically target early spiral galaxies, building a statistical sample large enough to determine whether Alaknanda is exceptional or representative. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will conduct wide-field surveys that complement Webb's deep, narrow observations. Together, these observatories will map the evolution of galaxy morphology across cosmic time with unprecedented detail. Ground-based extremely large telescopes, including the European Extremely Large Telescope and the Giant Magellan Telescope, will provide higher-resolution spectroscopy, allowing astronomers to map the internal dynamics of early galaxies in exquisite detail. Theoretical work is advancing rapidly. New simulations are being designed with enhanced resolution and more sophisticated physics to see if they can reproduce early spirals. Machine learning algorithms are being trained on Webb data to identify subtle patterns that human researchers might miss. The implications extend beyond galaxy formation. Understanding how quickly structure can assemble in the early universe affects our interpretation of dark matter, dark energy, and the fundamental parameters of cosmology. If galaxies form faster than expected, it might indicate that the universe was denser or more inhomogeneous in its early epochs than current models suggest. For astrobiology, the existence of mature galaxies so early implies that planets could have formed earlier than previously thought, potentially extending the timeline for the development of life in the universe. Every answered question generates new mysteries, pushing the boundaries of our cosmic understanding ever outward. Alaknanda stands as a testament to the power of human curiosity and technological innovation. From the mountains of India, where its discoverers worked, to the L2 Lagrange point, where James Webb observes, to the ancient cosmic epoch, where the galaxy itself shines. This discovery connects cultures, technologies, and timescales in a profound narrative. We're living in a golden age of astronomy. Instruments like James Webb are not confirming what we thought we knew. They're revealing a universe stranger, more dynamic, and more surprising than our theories predicted. Alaknanda, with its impossible elegance and premature maturity, challenges us to think deeper, calculate more carefully, and remain humble before the cosmos. The universe, as Carl Sagan reminded us, is not only stranger than we imagine, but stranger than we can imagine. If you want to follow along as we unravel these cosmic mysteries, hit that subscribe button and ring the notification bell. We're covering the latest discoveries in space and astronomy as they happen, breaking down complex science into engaging narratives. The cosmos is revealing its secrets one galaxy at a time, and thanks to missions like James Webb, we're all invited to witness these revelations. Until next time, keep looking up, keep questioning, and keep exploring the infinite wonders above. This video is based on peer-reviewed scientific research, published in December 2025, and official data from the James Webb Space Telescope mission. The Alaknanda galaxy discovery was made by Dr. Rashi June and Dr. Yogesh Wardadekar from the National Center for Radio Astrophysics in Pune, India. While every effort has been made to accurately represent the current scientific understanding, astrophysics is an evolving field. Interpretations may change as additional data becomes available. This content is intended for educational and entertainment purposes. Viewers interested in deeper technical details are encouraged to consult the original research papers and NASA's official communications.